Okay, so in this case, let's just say I'm not interested in the zeros and the poles, although it's going to compute them for me. So I get my numerator and denominator, and now I want to plot them. So it's basically like entirely equivalent to what we've seen before, but instead of using freq z, I'm going to use freq s, which is because I'm dealing with an analog filter and not a digital one. So anyway, it's just a subtle difference, but I just want to show you that if I look at my plot, super. So this is just the this is the magnitude, and I guess if I let it finish plotting, it's going to plot the phase in the bottom. Should I let it finish? All right, let's just let it finish. Go. So you can see that it satisfied all my criteria. So in the passband, it's totally flat. Now I told it that my passband needs to be at least at 1,000, right? So in other words, I can't have everything has to be greater than -3 decibels below 1,000, and I have that, right? Everything below 1,000 is well above 3 decibels, so that's good. I satisfy that criteria. And my other criteria was that at frequencies greater than 5,000, I need at least 60 decibels of attenuation, and it accomplished that for me as well. All right, so you can see that the shape of the Butterworth filter, so this is one of its qualities, it's totally flat in the passband, whereas the other filters don't have that. The price you pay for it is your roll-off could be much steeper if you use one of the other filters. But in the passband, it's totally flat. So all my frequencies in the passband will get amplified with exactly the same amount, which is a very desirable quality, again, depending on your application. All right, so now let's go back to the very first question we looked at where we talked about increasing the stop band and the pass band. So for this filter, we were told that MATLAB predicted we needed a fifth order filter. So essentially now what I'm going to try to do is convince you that the stuff we talked about before is correct. So if I keep everything the same, but now I'm going to change my high frequency cutoff, I'm going to change it from 5 kilohertz to 2 kilohertz. Should I expect my filter order to go up or down? Ooh, very good. All right, so I'm going to change that to 2 kilohertz, and I'm going to run it. And if I go over here to the window, it tells me that now I need a 10th order filter. All right, so more restrictive. Okay, very good. So let's put that back at 5. All right, now we're back to the original filter. Now let's look at the attenuation. Originally I said I wanted everything above 5 kilohertz to be divided by at least 1,000. Now let's say it only needs to be divided by 10. So I'm going to change this to an attenuation of 20 decibels. Should I expect the filter order to go up or down? Down. It's less restrictive. Okay. So I run that, and there's my filter, and now my filter order has dropped to 2. So to me, it's good enough that even if you don't understand the equations, you at least, if you say, well, I need a more restrictive filter, you know that the order is going to go up or down in some sort of predictable fashion. That to me is the most important part. Let the tool do its job. You know, there's no point in rehashing all the math that MATLAB is going to do. Okay, let's actually I wanted to show you just for fun. So those zeros and poles that I computed and ignored. Let me just take these out of uncomment these. So when you learn to design analog circuits, hold on, that's only a filter order of 2. Let's go back to a much higher filter order. Let's say we want this to be 80. So you should have learned when you design analog circuits how to create circuits that give you poles and zeros in different locations. You know, it just depends where you put your cutoffs. So this is the pole zero diagram, and so if you were actually going to design a circuit, you would just need to design a circuit that puts those poles and zeros in those locations. And what you notice always with poles and zeros is that they're complex conjugates. They always come in complex conjugate pairs. So you can see that they're paired symmetric across the x-axis. And the other key aspect of your Butterworth filter is that those poles always fall on a circle, right? And that's not an accident. So Butterworth filters, your poles always are on a circle. That's like basically the key defining characteristic. Okay, so we looked at Butterworth. So now let's look at the elliptic filter, which is essentially the same idea, and it's got more or less the same built-in MATLAB functions, but the filter's going to look different. So elliptic, let's open that. All right, so same thing. Our goal is to design a low-pass elliptic filter with a cutoff of 1 and a stop band that starts at 5. So it's the same thing. I'm going to set it up exactly the same way, but now instead of having a Butterworth filter, I'm going to tell it to tell me what the order is of my elliptic filter. So let's run that. So now it's telling me my filter order is 3. So that's the first interesting thing. Before, when I was dealing with the Butterworth filter, for those same parameters, I needed a 5th order filter. So now for the elliptic filter, I only need a 3rd order filter. So it's inherently a lot more efficient. But what price do we pay for that? So you have the gain in the top window and the frequency in the bottom window. So you can see that we satisfied all our criteria. In the passband, everything below 1,000 hertz is no more than 3 decibels away from being flat. So that's good. We got no more than 3 decibels of ripple. But there's ripple now. There wasn't ripple before. So what does that mean? Now in the passband, different frequencies are going to have slightly different amplifications. Is it a problem? Depends on your application. Now my other criteria was that everything below 5,000 hertz, everything at frequencies above 5,000 hertz should be attenuated by at least 60 decibels. Did I achieve that? Yeah, I did achieve it. I mean, it actually turns out that we hit the 60 decibel mark below 5,000, but that's okay. I basically didn't specify what happens in the middle. I just said, to the left of 1,000, I want this to happen. To the right of 5,000, I want this to happen. In the middle, you do what you want. If you zoom in on it, you can see that, just to show you that there is a good deal of ripple there. So it varies a lot. All right, if I change my ripple from 3 decibels to 1 decibel in the passband, is my filter order going to go up or down? It's going to go up, absolutely. So let's try that. Change that to 1 decibel. I tell it to plot. And it looks like we got a 4th order filter, so it went up by an order of 1. And sure enough, now we can see that my passband is much flatter than it was before. Let's see if we can get a zoom on that. So much snugger there. Again, totally depends on what the application is. And this is pretty cool. I mean, MATLAB actually figured out to make it go pretty much exactly right through that corner there. Right? It got it just perfectly. So that's it knows what it's doing, I guess, to put it dumbly. Okay, any questions on that? Who's going to be surprised to find out that the poles of the elliptic filter sit on an ellipse? Not an accident. Questions so far? Let me see if there's anything else I wanted to pull out of this. I think that might have been just about everything I wanted to talk about as far as the anti-aliasing. again, it's always the take-home message is that MATLAB will crunch a lot of the numbers for you. So always use the tool to crunch the numbers. There's really very little point in repeating that effort. And yeah, that's about all I was going to say. I was going to show you an example of a linear filter. I didn't get around to creating an example of that, but you know, the diagram we drew by hand was reasonably accurate for that. Mm-hmm. Yeah. I'm sorry? Yeah, exactly. You just leave it off. Right? You can design a elliptical digital filter, and that would wind up being a finite impulse response filter. So, but then I guess just the way MATLAB computes the filter coefficients, it knows that it's dealing with frequencies that go from 0 to or minus pi to pi, as opposed to in the analog domain, those frequencies go from 0 to infinity. So if I put in 5,000, it knows what I'm talking about as a frequency. It's just a flag, so it crunches the numbers properly. Yeah, and really the only other difference was that I used freq s instead of freq z, because the numerator and denominator are coefficients of an analog filter, so not a digital one. Again, it just crunches the numbers slightly differently to make it all work out. Did everybody notice where my poles and zeros were in both cases? Or I guess I didn't have any zeros, where my poles were? Left half plane, is that familiar to anyone? Oh boy. Okay, always, always, always. So this should be a lesson from your analog books. So this is like one of those cardinal rules. Where are we going to put it in so nobody forgets? Pink. There we go. Stable filters. In the analog domain must be in the left half, must have poles in the left half plane. Exactly. I'm sorry?
So that responses means output is not infinite, gain is not infinite for any positive frequency.
Correct. Right. If you wind up with poles in the right half plane, there'll be certain frequencies for which your output will just get bigger and bigger and bigger and bigger and become an infinite. So the cardinal rule for stability is poles in the left half plane. And if we went through all four of these different combinations of Chebyshev and elliptic and Chebyshev 1 and Chebyshev 2, the distribution of the poles might be different, but you're always going to find that they're in the left half plane. That's one of those rules. There's basically two rules: left half plane and complex conjugates. You'll never beat those two rules. And actually, that's initially how I knew I was doing this wrong when I was working on this earlier today. Is the poles kept plotting in the right half plane, and I didn't know what I'd done wrong, but I knew for sure there was something wrong. And eventually I figured out that I wasn't using the S flag to tell it that I was dealing with analog instead of digital. But you know, if they're in the right-hand plane, there's a problem. Okay. Any other questions? Good. I didn't want to dwell on this too much, but I felt that it's important to talk a little bit about where these filters come from, what they're good for, because you really can't have a conversation about digital filters without knowing where they come from. So you always have to anti-alias, or you have to oversample by a grotesque amount. But for practical reasons, we just don't do that. Okay. You want to take a 5-minute break? Now it's actually exactly halfway through, so why don't we do that, and then if you want to get a coffee or whatever you need to do, and then we will finish up.